Remember that the equipotential curves are perpendicular to the electric field lines, and the electric field lines point downwards towards a negative potential or towards a decrease in potential. And that's a very specific relationship. And it turns out that we can actually use that, not directly, we're not going to derive it from first principles exactly, but we can use that relationship to actually get a change in potential based on the electric field, and more specifically based on the path moving in an electric field. So the idea is that in general, we get this equation, and again, I'm not going to derive this from first principles for you, but we have delta V is equal to negative path integral of the electric field dot product ds. So delta V is the change in potential as you go from the starting position on the path to the final position on the path. And the units are volts. Then remember, we're integrating as we move along the path from the initial position to the final position. And I'm just using the letter S to represent position. ds is a small segment of the path. And the direction of ds points in the direction that we're moving at that location where ds is located. Then E is the electric field at segment ds. Now, the electric field and ds are both vectors, so they have directions. And in order to get a scalar out of that, we need to remember that this is the vector dot product between E and ds. So when we're working with the electric potential and electric potential energy, luckily when we're working with those particular things, we don't have to consider direction. But when you're moving within an electric field, you will have to actually consider the direction of the field and the direction of the path segment. Now, depending on your particular prof, you might not have to use this general formula for very often. It turns out that for a uniform field, so that's a field that has the same value everywhere, this integral simplifies to negative E, the electric field, dot product delta S. So before we had to consider the path integral from SI to SF, in this case, delta S is just really S final as a position minus S initial. But again, we have the dot product and we have the electric field vector, and we'll get a scalar out of that that's equal to the change in potential, or the potential difference from the initial position to the final position.